Hello students, welcome back. We went through one example problem of hypothesis testing. And of course, one example is not enough, so let's do another. It's this example problem, which is of course continuation from, no, not this one. But I'm going to pretend that we didn't do this a priori, and we're going to start as a new problem. Please stop the playback and read through. So, what's the circumstance here? Average birth weight for babies is 3,300 grams. Average birth weight for the babies coming from women living in poverty is 2,800. And then a certain group of researchers in an hospital tried some new parental care program to improve this low birth weight for babies being born from women in poverty. And they were able to improve a little bit. 3,060 grams based upon the random sample of 20. Simple random sample of 20. Now, the hypothesis is, has there been a significant improvement? So what's the structure here? First, second, or third? All right, this is highly unrealistic. So let's get rid of this. So first or second? They want improvement, right? So they want higher birth weight. So it's got to be this one. Now, what is the mu0 value, the null? 3,300, 2,800, or 3,060? We're talking about babies being born from women living in poverty here, and this new parental care program is about women living in poverty. So this one does not apply because this is for average birth weight for everybody, including women from middle income or affluent families, and they will take care of themselves. Now, for women in poverty, that's the issue here. So we begin from 2,800, and we want to get better than 2,800. That means greater than 2,800. That's my aim. All right, and then we want level of significance as 0.05. So how would we start? Null value is 2,800, right? That's the null. You see, 3,060 came from sample. Null should come out of nowhere. The name suggests nothing was done. It's null. So this came from sample, so 3,060 is not the null. It's either this or that, but we are talking about women in poverty only. 2,800 is the way to go. This one is not really relevant here. All right, here we go. We have kind of like this, and then null is 2,800. All right? And then we want improvement, greater than 2,800. So where do I shade, right or left? The shading should be on the right because we want greater. So that's my x value there, right here. And this alpha is 0.05, 5%. That's the level of significance here. From here, I can find out my x value, the critical value. And once I find my x value, the critical value, I'll be able to compare that with the sample mean from this study. What's the sample mean in this problem? What's the sample mean? It's the 3060. It came from sample, you see? It came from sample size of 20. So 3060, that falls either here, too far away from null, so null loses, or there, close enough to null, so null wins. So close enough to null, that means no change. So this new parental pair care program didn't do too well. We may have an illusion of improvement due to small sample size, but maybe not worth spending our resources for this new innovative program. Now, if it falls here, then alternative wins, which means there is significant difference toward better. So, okay, this new parental care program is worth spending our resources on. So that's the kind of setting we have. And let's do more mathematics. Okay, here we go. First, the critical value method. Here's the setup. And based upon this, here is the initial picture. Always begin with a picture. Normal picture, centered at the null, and we want greater, so improvement here, and we want this x value. And once you find x value, you're going to compare it with 3060. All right, how do you find your x value? Z-score is end minus center over SE, isn't it? And that has to be approximately equal to Z-score associated is to alpha value of 0.05, 5%. So 5% here to the right means 95% here. So looking up the Z-table, where's Z-table? Let's go to, Z-table. Let's go to the second page and 95%. Where is it? Yes, right here. .64, 1.65 is a push right here. So 1.645 is the way to go. This is one way to do. Another way is to look up 5% here in the first page and do the same thing. And of course, negative 1.64, negative 1.65, but it's to the right, so drop the negative. You can do it like that as well. Either way, you get 1.645, 1.645, and that's going to be the equation to solve. Now, end minus center over SE. I'll be bigger font here. End is the critical value you're looking for. Center is the null value. And what is your SE? It's standard deviation over square root of n, 500 or square root of 20. So 500 over square root of 20. And from here, solving this equation is not going to be too bad. So x is approximately equal to 2800 plus 1.645 times 500 over square root of 20. That's approximately equal to what? I got 2983.92. Even if I take 2984, 3060 is clearly greater than that. So this value here, 2984, so 3060 falls in the red region. Oh, there was improvement. Alternative wins. Here's the computation we just did. And here is the conclusion. 3060 fell beyond the critical value into the null region, into the alternative region, excuse me. Null region is closer to null, mu 0, and alternative region here. So we're going to reject the null hypothesis and we're going to accept the alternative hypothesis, which means, oh, there was an improvement. There was statistically significant improvement. So we're going to continue supporting this new parental care program to improve the newborn baby's health from family of poverty. This is how you work out the critical value method. Computation aside, it's like this. Null and the critical value, which come from alpha value, to the right. Find out the critical value and compare that with observed sample mean. Sample mean is too far away from null, then null loses. Close to null, then null wins. So the conclusion is very easy to make. Close to null, null wins. Far from null, null loses. A great reason I like the critical value method. Now, how about the probability value method, which is a little bit more sound in terms of theory? No, not even that. I'll say it's push. Same setup and same hypothesis. Here is the initial picture for the probability value approach. 2800 and then just x bar 3060 and find out the probability value, the p-value. Now, the question is, what do I do after finding the p-value? P is greater than alpha, then what? P is less than alpha, then what? What do you mean by p greater than alpha? What do you mean by p less than alpha? You see, that's a little bit hard. Nonetheless, let's pursue it. So z-score is x minus mu over SE, or end minus center over SE, 2.24. And if you look up your z-table with 2.24, it's going to be about this, 0.026 something. Okay, and 0.127, I guess. This one is a little bit more accurate because I use Mathematica to calculate instead of the z-table. So it is less than the alpha value, but what does that mean? It means the probability for type 1 error is less than the threshold. What is type 1 error? You have to remember, type 1 error is the probability of error rejecting the null even though it is right. So that danger is pretty low. So we're going to go to alternative. Did it make sense? If you understand type 1 error, type 2 error, all the conditional probabilities, that must have made sense. If you're a little bit hazy, oh, that explanation probably didn't make it. So if I give you a bit of a shortcut, which is not completely right, and you can consider P as roughly speaking. The probability that null is right. So if this is large, then we're going to get the null. And if this is small, like this, then we're going to go to alternative. So the probability that null is right is pretty small. It's less than alpha. So it's got to be wrong. Let's go to alternative. It's a bit of a cheating because this is, as I said, roughly speaking, and it's not really correct, but most of the time it works. But still, my preference is critical value approach. Anyway, here's a complete picture. Probability is pretty small, less than alpha, so reject the null and accept alternative hypothesis. Now let's go back to the critical value approach. The reason I'm going back to critical value approach again is because of my experience. I've been teaching this in 3011 and also in 1000 level a lot. And the students who use critical value methods usually score the best in terms of course grade. And students who go with probability value approach usually end up badly. So I'm going to drive my students toward critical value approach a little bit more. So from the initial picture, the null, critical value, and then alpha, and then find out critical value using the Z computation. All right, and then compare. And then compare. So this observed mean falls either here in the blue region, close to null, so null wins, or the red region, far away from null, so null loses. With this kind of geometrical intuition, you can't miss it. This is easy to understand if you follow. The other method is actually pretty hard because you have to go through the idea of conditional probability and type 1 error. So a bit of a cheating was necessary. P was, roughly speaking, the probability the null is right. Still, it was hard to understand that way. This one, on the other hand, is not difficult to understand at all. All right. So much for this example. Now, do we have a two-tailed test example here? Same thing, parental care program, and then we just do just like confidence interval, 2.5% here, 2.5% there, and see if 3060 falls in the blue region or red region. Blue region, then null wins. Red region, null loses, basically. But we are doing two tails, not one tail. That's basically it. Okay, so much for section 1. And in sections 2 and 3, we're going to deal with a bit more realistic setting. That is, when we don't know sigma, what we do.